Hi, we're Muscle Motive Motors, and here's our ES50 final project. To describe our project in one sentence, we can say that it's an Internet of Things EMG controllable robot. EMG stands for electromyography and is a tool to measure muscle response in the form of electrical activity in response to a nerve's stimulation of the muscle. To make our project work, we're processing and transmitting the signal wirelessly to drive two electric motors at the same time via an H-bridge DC motor control element. We're very proud of our project, and here's why. It actually works. This is Dennis, our great electrical engineer, that demonstrates how the car actually works in action by flexing his forearm muscles. He can actually control the car and move it forward. We're very proud of this, and let's get to the specs. As with many projects, we spent most of our time troubleshooting errors that emerged throughout the process, but in the end, we do have a fairly elegant solution for a wireless system consisting of two Arduino R4 WiFis for computational control and two All-MX EMG shields to capture, process, and transmit the analog signals from the muscles of the participant. Here's a high-level abstraction of the circuitry that allows for the functionality of our project. With regards to the actual actuation of the electric motors in our robot, we learn about and use the concept of pulse width modulation. Pulse width modulation enables control over the average voltage delivered to an electronic device by rapidly switching the power on and off. The resultant average voltage is determined by the duty cycle, which is the proportion of time the power remains on compared to when it's off within a single cycle. To alter the direction of the motor's rotation, it's necessary to reverse the current flow through the motor. This is commonly achieved using an H-bridge circuit consisting of 4 switches and MOSFET transistors arranged around the motor in a configuration resembling the letter H. By simultaneously activating a specific pair of switches, the direction of current flow and consequently the motor's rotational direction can be altered. Combining pulse width modulation for speed control with an H-bridge for directional control offers comprehensive management of the DC motor in our case and turned out to be a great solution to make our project work seamlessly.
For our code, we decided to use Arduino Cloud. Arduino Cloud is an online version of the regular Arduino IDE that allows us to transmit data via the internet with ease. We decided to split up our code into two parts for each Arduino. We have the code that captures and processes data from the EMG signal, and another that makes the physical motor active. For the EMG sensor Arduino, we capture raw analog signals from the EMG sensors at a rate of 20 readings per second. Then we process this data with a standard deviation calculator here to ensure smooth transitions between our values. Then we map the standard deviation to the corresponding speed of the car. The higher the standard deviation, the higher the speed. However, for the sake of simplicity and easier performance in practice, we implemented a threshold that simply puts the motor in active or inactive form. This data is then transferred to the Arduino on the car via the capability of cloud variables, as seen here. The code then assigns when the motor is active or inactive, creating wireless communication with our car.
Our original idea was to have each wheel's RPM correspond to the strength of the muscle flexing. While this worked to an extent, the user had limited control over the car's movement due to delay and sensitivity issues. We wanted to create an arena for the car to move through, which would be difficult to maneuver with the first model. We decided to sacrifice the code complexity of our design to gain greater and more accurate control of the car by creating a second version of the code. The team altered the code to be more binary. The EMG sensors detected whether muscles were activated or not. When the muscles were activated, the code turned on and the speed was set to 150 out of 255. There was some bleeding of values from the left arm over to the right as well. When the left arm was flexed extremely hard, it would be detected by the right sensor too, causing the right wheel to falsely turn. To fix this issue, we edited thresholds in the code to prevent any bleed over. Future applications of our project include an alternative way to drive motor vehicles. Specifically, people who are unable to drive a car conventionally could use our design project. By placing electrodes on any muscles that can contract, people with limb disabilities can still drive a car. We tested this ourselves by placing electrodes on other muscles of the body, and we were still able to maneuver the car around well.